Hello everyone, we are choosing to assess this specific soap dispenser and believe it or not, it was a lot more challenging than I thought. There's a lot more moving parts than I imagined. This is actually our second model because our first one I misplaced some very key parts to the functionality of dispensing soap, so I had to get a new one. I'm blaming it on my 2-year-old son because I can. But this one has the same top, so we can build our prototype off this one and connect it to this one, have a functioning piece.
The soap dispenser is made of 3 main subassemblies: subassembly 1, 2, and 3. Subassembly 1 is comprised of the valve chamber, gasket, downstem, spring, and ball. Subassembly 2 is comprised of the nozzle, plunger, valve stem, and top valve. Subassembly 3 is comprised of the body and the cap. The soap dispenser moves soap from the body through the nozzle by the use of 2 one-way valves. One one-way valve is comprised of the chamber, spring, and ball at the bottom of the valve chamber. The other one-way valve is comprised of the top valve and the valve stem. When subassembly 2 is inserted into subassembly 1, it creates a tight interface. When downward force is applied, the ball valve closes, preventing soap from returning to the body, and the top valve opens. This allows the soap to flow through the valve, up the plunger, and out of the nozzle. When the downward force is taken away, the spring returns the nozzle, or subassembly 2, to its original position. In doing so, subassembly 2 closes due to the suction, and as it returns to its upward position, the suction opens the ball valve, allowing soap to refill the chamber as subassembly 2 returns to its original position. The cycle of function is repeated, and it continues to empty and fill the chamber. The soap dispenser is fully assembled by taking most of subassembly 2 and inserting it into subassembly 1. This can then be press fit into the cap and threaded into place. The nozzle is then press fit onto the top, and the soap dispenser is fully assembled.
Laid out in front of me are all of the parts for the soap dispenser assembly. Here on this left side, all of these parts were injection molded. That is made by melting a thermoplastic and then using a reciprocating screw to inject into a mold where the piece was cooled and then removed from the mold. These 2 parts, the cap and the nozzle, both had a secondary operation done on them where a spray luster coating was provided for aesthetics. This part, the body, was blow molded, in which a drop of plastic was put into a mold and then air was injected into the top forcefully to make the part expand to fill the mold, and as the part cooled, it was removed and rotated to retain the threads on the top here. These 2 parts are stock parts. This is the gasket and this is the spring. The gasket was stamped out of a foam sheet of stock using a steel roll die cutting technique. This spring here was made from cold drawn wire that was further cold worked using rollers to create this helical geometry here. From our DFA analysis, we decided to implement two different design changes, both of which are combining two parts into one single part. Therefore, you have less part interfaces and less possibilities for error proofing, thus decreasing our error proofing metric. We decided to combine our valve chamber and our downstem, as well as our nozzle and our plunger. The valve chamber and downstem we printed as one part here. If you implemented these design changes for a 100,000 unit batch run, you would have $1.36 savings for each part, and that would amount to about 25% cost savings.
The original soap dispenser had 11 parts with 19 interfaces, giving it a design complexity of 14.46. The gasket is not required for the system to operate, therefore the theoretical efficiency was 90.9%. The gasket, however, is practical, giving us a practical efficiency of 100%. Our redesign incorporated the valve chamber and downstem into the valve chamber stem, and the nozzle and plunger into the nozzle plunger assembly. We also removed the gasket, leaving us with 8 parts with 13 interfaces. This brought our final design complexity to 10.2. All parts are required for the system to operate and are practical, bringing our theoretical and practical efficiencies to 100%. Our redesign resulted in a 30% reduction in design complexity, a 10% increase in theoretical efficiency, and a 32% improvement in error proofing. Of note, all other categories increased by 25%. This is due to a higher weighting of contributing factors.
Here we have our part that was 3D printed, along with the gasket already on, and some of the assembly already put together for ease of use. PLA plastic was used, although ABS plastic with injection molded would be used during the actual manufacturing process. One issue we had was with concavity when the 3D printer was printing up from here, which turned out not to be a huge issue. We were really proud of the way this turned out. The ball fits very smoothly in here, along with the spring. This part is attached to the body, with everything else fitting very smooth.
Alright, I took the core out of its body so you can see a better view of the prototype and like a workable test. There you go.